This is our last video for all of the chapters in our calculus book. This is 11.5 where we're going to be integrating inverse trig functions. So this is just the reverse of what we did in 11.4, which was differentiating these inverse trig functions. So what we are going to be doing is I'm going to introduce you these new rules of integrating inverse trig functions. But first, what we're going to do is connect the differentiation rules to those integration rules. So this is the review of differentiation of these various inverse trig functions. So when you take a look at these, what I'm going to do is a problem from your last set of homework problems. It's number 9, it's the version of number 9. So what I'm going to just do is use these rules right now. Oofda. So here we go. This is going to be where we have 1 over a is some sort of scalar multiple. So I'm going to pull this out, 1 over a, and then derive this actual function. Okay, the next thing that I'm going to be observing is I am going to be using this rule, and I do have a composition function here. I just don't have arctangent of x, which I'm deriving with respect to x. I have this x over a. So I am going to find my u, or identify my u as, and I'm going to rewrite this just a hair, as 1 over a times x. Okay, and then the derivative of that would be, or du dx, if you're going to derive some sort of constant times an x, remember the x is just going to cancel out. It's to the 1 technically, so drop down the 1 when you're differentiating. Subtract 1 from the exponent, so it's just going to be 0, so it's going to be 1 over a. Okay, so it's just as the same as if you had 1/2 times x, it would have just been 1/2. Okay, so I am going to now apply this. I'm first going to derive arctangent, and the derivative of the arctangent function is going to just be 1 over 1 plus, and then just leave that inner function alone. So here I have it. I'm going to have that 1a, there's my scalar, times, and now the derivative of this is going to be 1 over 1 plus, and then that inner function left alone, x over a squared, and then times, and then now this is where you're saying derive that inner functions and multiply it. So here we already did that. It's 1 over a. Okay, so sorry, this got squished a little, but that is 1 over 1 plus, and then x over a squared. So I'm going to simplify this a bit. I'm going to combine those. It's going to be 1 over a squared times 1 over, and then 1 plus, and since this was x over a squared, I'm just going to have x squared over a squared. Okay, so here is also where I'm going to simplify this a hair further. I'm going to now take this a squared and distribute it. So what I'm going to get is 1 times 1 on the top, and then when I distribute this a squared, it's going to be a squared times 1, so just a squared, plus a squared times x squared over a squared. Those would cancel each other out. What I'm just going to get is x squared. So here is what I'm looking at. So that was from yesterday, or from the previous section. So now I'm going to kind of just use this for our new integration rules. Oops. Our new integration rules are as follows. So I'm going to just bring this up. If you have 1 over and then an a squared plus an x squared, that's a key thing to look out for. We have something squared plus something squared on the bottom. That's going to be a key indicator that you're going to be using one of these rules. So perfect squares plus another perfect square, these rules right here is what we're going to use. So here are our new integration rules. We're going to be using that differentiation of these arc, or of these inverse trig functions that we just looked over, and we're going to be working them backwards. So in this last process, what we had done was this problem right here, and we got that 1 over a perfect square plus a perfect square. That's this right here. So if you have some sort of perfect square plus perfect square, and then the derivative of that some sort of inner function squared up on the top, then you're going to have this equation right here to look at. Okay, and then same thing, we only have 3 for these arc functions. These ones are the main ones that we're going to be using. Alright, so we're going to do some of these problems. Number 9 is the one that we're going to do, and we're going to do this from 11.5. So we just did a number 9 from 11.4, we're going to do one from 11.5. What I would hope you would see here is this is something where we have a perfect square minus a perfect square going on, so that's when you're probably going to have to be using one of these. Okay, so observe the pattern that you have here. It's mostly going to identify with this right here. Okay, so I'm going to rewrite this. I'm going to write this actually off to the side, so I have enough room. Okay, so if you identify that pattern, it's going to be equaling 1 over A times arc secant, absolute value, A plus C. Okay, so we're going to be using this right here. And I copied that directly off of one of our new rules. So to begin, what I would like you to see here is that we have this 4x squared. You're going to want to rewrite that. And then you also have this minus 1. 1 is also a perfect square. So I'm going to have to clump this all together as a square. So being that 4 is, I'm going to just go ahead and basically take this 4x squared and then rewrite it. So I'm going to rewrite it as this. 1 over x times, and then in parentheses 2x squared, because that way we have matched this right here, that we have a perfect clump that's squared. Okay, because here, I mean, we don't have a rule that's saying 4 some sort of number times and then u squared. We're just saying that there's some sort of function squared. So there is that function that's squared. That is our inner function. That is our u. And then I'm going to have to expand this minus, and then technically what I'm going to have to do here is they have a minus something squared. 1 is a perfect square, so I can go ahead and just rewrite it as that. Okay, don't forget your dx. Now, as we're doing these integration problems, our process is always thinking, all right, try to match it up to one of these patterns, and then what our process looks like is that we're going to have to come up with an equation that links u to x, because what we want to do is take out all these x's and replace them with the u. So as we rewrote this, I hope you could see that this u became this 2x. So here we have u is equal to 2x. Therefore, du dx is equal to 2. Okay, and we need to do that also because, again, we have to take out this dx somehow. So this this differentiation process allows us to do that. We get an equation that links u and x, and we get an equation that's going to link du to dx, because what I'm going to do is just multiply that dx to both sides. So what you're going to hope for is that we can take out that dx and replace it with this. Okay, and you can see that it's not quite matching, so I am going to divide by 2. So 1/2 du is equal to dx. Alright, this is what I'm going to use. Out with the dx, in with the 1/2 du. Okay, also what you may have to do sometimes is rewrite these, but I think we're going to be okay as we have it here. So actually no, we're not. So I am going to rewrite this. We're going to have to take, say, this x right here needs to be replaced as well. So I want to find out what just x is. So this is where we would divide both sides by 2. So x is equal to 1/2 u. Okay, so these 3 equations, and we've had to manipulate a bit, but we're going to be able to replace all of our x's and all of our dx's with something with a variable of u. So I'm going to rewrite this. We have x, I'm going to replace it with 1/2 u. And then underneath this radical we have u squared. That came from this equation right here, minus 1 squared. And then du was times 1/2 du. Alright, so we don't quite have it matching this completely. I have this 1 over 1/2 that I'm going to have to pull out, so I'm going to do that right now. Keep in mind that this thing right here is 1 over 1/2 because we have that 1 on top. Okay, the other thing I'm going to pull out is this 1/2 times 1/2. Okay, so basically we have 2 times 1/2, so that's going to actually just cancel each other out completely. But now we have left over, when we pulled out those scalars, u times u squared minus 1 squared du. Okay, so now we have this matched exactly. So observe that we have our u is equal to 2x, and then our a here, what was that perfect square? A is equal to 1. So I'm going to rewrite this using this rule exactly. This is all equal to 1 over 1 times arc secant, and then the absolute value of our u, which we said is 2x, all over a, which is just 1, plus c. Okay, so this is all in all just equal to arc secant, absolute value 2x, plus c. Okay. Alright, number 15, they get tricky on us fast here. Number 15 is trying to integrate this particular function right here. And what you're going to notice is this does not align with any one of these up here. Because yes, there is the square root of 1 minus a perfect squared, so 1 squared minus a perfect square. So it would follow possibly under this. However, what we have to identify is, well, our u in this case, or our a function that's being squared is just x. So u would equal x. And if we derived u and derived our x, we're going to not get arc sine of x. Okay, there's nothing about this that would match up with this particular integration. So this is out, even though it looked close. The other thing that we do not have is, any possibility. We have one other rule, integration rule. Whoops. We have one other integration rule. It looks like this: 1 over u times du, that has a quotient in it. So we could try to match this up and say, all right, let's try to hope and set this whole bottom equal to u. And if we differentiate that, this 1 minus x squared to the 1/2, if we differentiate that, we're going to hope that we get this du on the top, or the derivative of u on the top. However, once again, we do not. If you were to let u equal 1 minus x squared to the 1/2, this would require the chain rule and all. We would just get 1/2 1 minus x squared, and then leaving that inner function going to the negative 1/2. And then we could go in and multiply by the inner function's derivative. So here is du, and what you can see, or du dx, so we just derived u. What you can see is that has nothing in common with this. So this is also out of the picture. So this is where you're left to, you've kind of done a process of elimination. These are out. This one's out. So what we're going to be left with is rewriting. What I have done here is I have rewritten this integral then as a product of two pieces, so the arc sine of x times, and then this 1 over the square root of 1 minus x squared dx. And what I do hope that you don't try is, now if you were to take an integral of, if this arc sine of x, or this inverse sine of x, had not been there as a multiplier, then this definitely would be something that you would want to recognize as 1 over and then the square root of a perfect square plus or minus a perfect square. So that would have been something that you could have integrated. However, we have this multiplier of a function on, so we cannot do that. But what we have not tried is to let this be our u. And hopefully by these rules in our textbook, sorry you can't really see those, but all of these rules that we had before, hopefully by doing a lot of those problems, we can kind of see, oh yes, this arc sine, when I derive this, will have some sort of relationship to this 1 over a square root of 1 minus a perfect square. So I'm going to do that right there by using the rules that we just showed you, du dx. So when I go ahead and derive this u, because I have a u that links an x to it, so I have an equation that links u and x. What I am going to try to do now by deriving u is get an equation that will link du and dx so that I can get rid of this thing. And in the process, you hope that it will address this. And so it does, because when I derive arc sine, it's going to be 1 over, and then the square root of 1 minus, and then that inner function, which is just an x squared. And then dx, the derivative of that inner function, the derivative of x is just 1, so times 1. But we don't need that. So here I'm going to rewrite it as du is equal to 1 over 1 minus x squared, and then times dx when you multiply that to both sides. So I have that in with this, out with that, in with this. Right there, that's our new du. Okay, so I have du here, and then the integration of 1 over the square root of 2 to 0. Arc sine is just u, and we do have a rule for this. This is just u to the first power, so what I'm going to do is integrate. I'm going to add 1 to the exponent and divide by that new exponent. So I'm going to get u to the second divided by 2, which is the same thing as 1/2. And then here, that du does drop out, because in the chain rule it would have appeared with differentiation, but in the integration that du will just drop out. So here, don't forget, I do have this 1 over the square root of 2, 0. This is where, though, you need to bring your u back out, or put your u back out and sub in what it's equal to. So this is all arc sine of x, and then squared, so I'm going to put a squared right here, and then 1 over the square root of 2, 0. So here's the thing. This is the fundamental theorem of calculus right here. This is not an indefinite integral, so we didn't need the plus c, but we do need to use the fundamental theorem where you plug in this, you plug in that. So I'm going to have 1/2, and then maybe I will just put this whole thing around arc sine of 1 over the square root of 2, which isn't a proper way of writing it, honestly. But okay, so here's squared, and then minus 1/2, and then this thing, arc sine of 0, all quantities squared. Whoops. So now this is where you're going to resort to your unit circle. I'm sorry, this right here is the same thing as the square root of 2 over 2. So you're going to ask yourself, on the unit circle, when we're looking at arc sine, we're only interested in this portion of your unit circle. So it's either going to be this angle or this angle that we're interested in, and we're going to be interested in this positive one, not the negative one. So we have 1/2, and then that angle right there is pi fourths on our unit circle. So once again, look at your unit circle and ask yourself, what angle, when you take the sine of it, are you going to get 1 over the square root of 2, or in other words, the square root of 2 over 2? And it's going to be those 45 angles. So that's going to be squared minus 1/2. What angle, when you take the sine of it, do you get 0? There's only one that's in that range. So it's this one right here. You get 0 squared. So here I am going to go ahead and get pi squared over 4 squared, which is 16, times 1/2, and then minus 0. All of that's just 0. So we're going to get pi squared over 32. Done. Through a process of elimination,